Hi everybody. This is a short supplemental video for mechanics of materials. Some of your classmates have expressed some difficulty with the homework from the handout the handout is labeled chapter 16, but the topic is Mohr's circle. And so what I have done is I've taken one of the problems, 16.7, that will be very similar to the problem that you will see on your final exam that will be worth 25% of your final exam grade. And so I just want to go through this with you step by step. For problem 16.7, it says use the transformation equations on the biaxial state of stress below to determine the state of stress at theta equals 17 degrees, 30 degrees, and 60 degrees. They tell you that the normal stress, sigma in the x direction, is 5,000 psi in compression, which is a negative 5,000. That sigma in the y direction is 1,500 in tension, which is positive, and tau xy is 3,300, which is positive or negative depending on how you look at it, depending on how you define positive or negative. Tau xy, shearing stress, is a function on a plane rather than on an axis. So it's going to be counterclockwise rotation in one direction or on one set, like the vertical faces, and then clockwise on the horizontal faces on a stress block, or vice versa. And so as long as you choose that properly, you will be fine. So the first thing that you do with a problem like this to find the state of stress at an angle, which I did it for 17 degrees, which will get you through the rest of the problem and through the problem on the exam as well. But you have to first draw a stress block similar to in 16.8. So I'm going to go back up to my handwritten solution, and you can see that I've written out those three stresses, sigma x, sigma y, and tau xy. I have defined tau xy as being positive in the counterclockwise direction. You could define it the other way as long as you're consistent, but we will use tau xy as being counterclockwise positive, clockwise is negative. Okay, the next thing you do when you draw a state of stress, you start with the stress block. You choose one of the faces to be the face of interest, and then you work from that all the time. So I tend to choose the vertical face on the right as the face of interest, but you can use any of the four faces of that stress block as long as you're consistent with your arrow markers. So in the x direction, sigma x is along an axis, so x is horizontal. It's 5,000 psi and it's in compression, which is negative. Sigma y is on the y-axis, which is vertical. It's 1,500 psi in tension, so that's positive, pulling away. And then tau xy I've defined as on my face being positive. So this arrow and this arrow on the vertical faces, if they were left to their own devices, they would result in a counterclockwise rotation, whereas the arrows on the horizontal faces would result in a clockwise rotation. And they have to balance out. If they're both going in the same direction, then the block is actually, you're saying the block is going to spin, which is not the case for a state of stress. All right. So the next thing that we want to do is to start to draw Mohr's circle. And if you go back to the page out of your book, right before this shows you how to do the construction. All right, there are two equations that you need to use. You need to use the equation for the radius of the circle and then for the coordinates of the center of the circle. So that's what I've done next. And I've plugged in the data that I have to those equations, and I found the radius, sigma x minus sigma y over 2 quantity squared plus tau xy squared raised to the 1/2 power will give me the radius. So you have to remember sigma x is negative, sigma y is positive, so negative minus a positive is just minus minus. Come out with this number, and the radius of the circle turns out to be 4,631.7 psi. The center of the circle, because on the principal stress axis, which is the axis in the horizontal direction when we draw Mohr's circle, where we have sigma max and sigma min, tau is always equal to 0 at that point. And you can go back to chapter 2 in our textbook and show that this is true. What we're really talking about is a case where all the stresses are either pulling or pushing at that particular angle. So tau xy is 0 at that point. So the circle is centered at some coordinate on the sigma axis and 0 on the tau xy axis. So that value is sigma x plus sigma y over 2, and the coordinate of the tau xy, the center of the circle on the tau axis, is always 0. So I come up with coordinates of negative 1750 psi and 0 psi. So now I have enough data to draw a circle because I know where the center is and I know what the radius is. All right, so moving down, I construct a circle. This is my sigma equals 0 axis. In other words, this is the origin of my coordinate system. This axis is sigma, it is not x. This axis is tau, it is not y. So the center at sigma equals 0, tau equals 0 is right here. All right. So then, oh, I'm sorry, that's not my center, that's the origin of the coordinate system. My center is over here, I found that above, where I have a coordinate of negative 1750, comma 0. So that's the center of my circle. Then I know the radius of the circle is 4,631.7 psi. So I've drawn that. What I usually try to do, and I do not construct a very nice looking circle, I like to refer to this as Mohr's oval, but if I were a better artist, it would be a circle. I construct a circle at that center coordinate that has a radius of the calculated radius, and I usually just draw 4 points on that circle, and then I connect them with what I hope or intend to be a circle. And that is the construction of Mohr's circle. Okay, so continuing with that idea, I guess I should explain this a little bit. Since the radius is the distance from the center to the principal stress, if I take the coordinate, the sigma coordinate of the center and add it to the radius, I'll get sigma max. And similarly, if I take the sigma coordinate and subtract from it the radius, I will get sigma min. Sigma max and sigma min are the values of the principal stresses of this circle. Now, since in the tau direction it's centered at 0, the radius is also the value for tau max, and it's also the value for tau min. Now, if you remember when we talked about how this circle is constructed, it's a transformation equation and it's a geometric construction. So 2 degrees on the circle equates to 1 degree on the stress block, or 1 degree in real life. So anytime that you have a rotation, for example, if you have 17 degrees, if that's 17 degrees in real life, it's going to be represented by 17 times 2, or 34 degrees on the circle. All right, so what I have done is, if you look at any time that you construct a right triangle with the center as the apex, the hypotenuse of that triangle is always going to be the radius of the circle, because that's the distance it takes to get from the center to the circle, to the edge of the circle. So it's sort of self-explanatory, but it's not necessarily obvious. Right? So we find those points, we construct our circle, and then we go about answering the question. It says, what is the state of stress at theta equals 17 degrees? Well, unless they give you better information, when they say 17 degrees, they mean 17 degrees from the cut face, whichever you chose the face to be on the stress block, to some other angle, and I always take it to be in a counterclockwise direction. So if I think about my cut face, how do I locate the cut face? All right, well, I know the values, don't I? I know sigma x, and I now know tau xy. So if I plot those 2 points on the circle, I'll come up with a point that will give me a right triangle. And I can find what this angle is using the tangent, opposite over adjacent. Or I could use opposite over hypotenuse. It doesn't really matter, but I have the 3 sides of the triangle because the hypotenuse is the radius. This is the value of excuse me, I just got a little sidetracked for a minute. This is the value of tau, and this is, from here to here would be the value of sigma, but from here to here is the center minus the value of sigma at that point. So you have the lengths of all three sides of the triangle. You can find this angle using a trigonometric function, and I found that the angle is approximately 57 degrees. Okay, now if I want to rotate counterclockwise, that means I go this way, right? I go to the, in this case, kind of to the left and down is counterclockwise rotation from the face. And I want to rotate down 17 degrees. Well, 17 degrees on the stress block is actually 34 degrees on the circle. So the angle here that I have would be the original 57 minus 34, or 23 degrees. All right, now I've drawn out that construction here, but I've also drawn it down here. I've redone it so that you can see it more clearly. All right, so here I am. This is the center of the circle. This is the x distance, the distance from the center to, not the edge, but to the x coordinate, or the sigma coordinate, I mean to say, of the edge. And then this to here is the y distance, right? So I know the radius, I know the angle, and I can use sine and cosine functions to find x and y, which I do. All right, now I want to find sigma, which I have to take that distance x and actually subtract, because I'm going to the left, from the sigma coordinate of the center, and that gives me my sigma, my normal stress at a rotation of 17 degrees on the stress block counterclockwise from my cut face, and tau, which is above the axis, so it's positive, at this distance of 0 plus y, because this is at 0 in the tau direction. It's neither up or down. It's on the main axis. And so I get the values, and those two values are the state of stress at a 17 degree counterclockwise rotation from the cut face. All right, so this is the type of problem that you're going to have on your final exam. If this is helpful to you, please use it in your notes and to do the rest of your homework. And if you need further help, if this doesn't make sense, please get a hold of me and I will help you through it. So having said that, that's the end of this discussion. This video is about 12.5 minutes long. So I think it'll be worth your time, and let me know what I can help you with. Thanks.